So it's now a pleasure to introduce the 2016 Gerald Whitrow Lecture. We've already heard the citation for the speaker, who is Dr. Neil Turok from the Perimeter Institute, Canada. The title is beautifully simple. It is Universe. You will have the abstract in the program. I'll just read one part of it, which is very appealing to a mere planetary scientist. It says, "The universe is astonishingly simple on the largest and the smallest observable scales, with great complexity in between." So, great pleasure to introduce Neil Turok, and I would just say I've already apologised to him. I have to leave. I will pass over the chair to the Senior Secretary, Ian Crawford, who will conclude the meeting. It's a pleasure to introduce Neil.
Thank you very much. Thank you very much for that generous introduction. It's really a pleasure to be here in one of these most famous of all scientific societies, so it feels quite a burden. And it's a double burden because I'm a theorist and I have to follow these two spectacular talks about the formation of galaxies and exciting exoplanets. Incidentally, I think the answer to that question about how it avoids the stuff in between us and the star is to design the spacecraft to be very long and very thin and to travel with a minimal cross-section. And if you lose 95% of them, well, 5% of them may get through. So there are some calculations indicating it may be possible. But I'm going to represent theory this afternoon. And what I want to tell you about is I have to sell you a difficult story, which is that we're in a crisis of the best possible kind. Okay? Crises, obviously are things we dread. But in the case of fundamental theory, there's really nothing better than a complete crisis, a breakdown in our fundamental assumptions. And I believe that is what's occurring right now. The theories of the 20th century have received have evolved to a point where they've reached their limit. Let's put it that way. And we've had a slew of observations. Just in the last 4 years, we've probably learned more from observations than we have in the previous 30. We have a slew of observations challenging theory at a very profound level. And this leads me to believe we're actually on the threshold of advances similar to those which happened in the early 20th century. As you know, classical physics, classical mechanics, electromagnetism were overthrown at the start of the 20th century because people realized they simply couldn't cope with some fundamental facts about the universe. And today we're in a similar situation. That's what I'm going to explain. So I'm going to spend a fair amount of time talking about this crisis and how deep it is, how severe it is. I'm going to explain to you that from my point of view, the most popular account or way of dealing with this crisis, which is to invoke a multiverse, and I'm very happy to see Bernard Carr here representing that line of thought. From my point of view, that's a failure. I'm interested in theories which are genuinely predictive and explanatory, and I think a multiverse doesn't pass that criterion. But I've got to put something in its place, and so the last part of the talk I will explain my humble attempts to do so. So the title of my talk is provocative. Deliberately, I am saying universe, not multiverse. And I will try to justify that. Well, here is the universe, beautiful picture. Here's the cosmic web we learned about in Andrew's talk, the formation of galaxies, stars, and of course the solar system in the middle. I'm most interested in the outer limits of this picture. This red edge here is the cosmic microwave background emitted to us nearly 14 billion years ago, which shows us the early universe as it emerged from the Big Bang. But I'm much more interested in what lies beyond that and what lies all the way out to the gray edge, which is the Big Bang singularity itself. And I'm going to end the talk by telling you about how we will see the Big Bang singularity observationally at some point in the future. This, of course, is the history. So that was a picture of the universe in space, the distribution as we look outwards. This is our picture of the universe, its evolution in time. It began very mysteriously. Everything came out of the singularity. And then as it cooled, it formed the atomic nuclei and molecules, galaxies, stars. And then at late times, the expansion of the universe has been speeding up due to the dark energy. This picture, which Andrew also showed, was made by the Planck satellite, mapping that outer red circle in fine detail and revealing the fluctuations which came out of the Big Bang and which gave rise to galaxies, stars, and planets. I was fortunate to get involved in this field in the 90s, where we calculated so this is the pattern of the temperature fluctuations, but we calculated the correlation between the temperature of the sky and the polarization as predicted from basic theory. And I take absolutely no credit for this. All the theory was worked out by Einstein and Chandrasekhar. In the early 20th century, we simply turned the handle into a curve of the correlation between the temperature and the polarization. So that's the theoretical prediction. There are no free parameters beyond the ones you learn from this graph, from fitting this graph. With no free parameters, you fit the data beautifully. So universe is simply staggering that using known physics and nothing inventive at all, we reproduce precisely how the universe works. It's the first sign the universe is, on large scales, actually the simplest thing we know of. It's as simple as the simplest atom in the universe. And here it is. So there are just 5 numbers you need to describe the universe. 3 of them describe the matter density. We have baryons, ordinary particles, ordinary atomic nuclei, and electrons, of course. Then we have dark matter, which is still unknown what it is. It's a major embarrassment, but it seems to behave rather simply. And Andrew showed how the dark matter clumps in a very predictable fashion. We don't know what it is, but we think we know how it behaves fairly well. And then we have the dark energy, the most mysterious stuff in the universe. And due to these wonderful observations, we know its density surprisingly well. So there are 3 numbers telling you the composition of the universe, the relative proportion of these types of matter, and 2 numbers telling you about the geometry of the universe on large scales. So again, Andrew emphasized we postulate very simple form for the initial variations in density in the universe. It is Gaussian random noise with almost the simplest of all possible power spectra, namely perfectly scale invariant. And I say almost because there's a slight deviation from scale invariance in the power spectrum of about 1 part in 30. So roughly speaking, we have the early universe with scale invariant Gaussian random noise. That's how it came out of the Big Bang, and that's what theory has to explain. Fundamental theory has to explain these 5 numbers, okay? And that it's staggering that the fundamental properties of the cosmos can be summarized so simply. The numbers at the top represent the state of the universe today. It's like the time in the universe. So we're not going to explain that number. We're not going to explain the time of this lecture, I don't think. But we do want to explain the properties of the universe. There are a few other numbers I'm not mentioning. The masses of neutrinos, for example, they can play a very small role, a very minor role in cosmology, and a lot of zeros. So the spatial curvature of the universe, for some reason, is almost 0. The equation of state of the dark energy is, for some reason, almost perfectly pressure over rho is W is almost exactly -1. We don't see any running of the spectral index, so there's no curvature of the spectral index with scale. We don't see any non-Gaussianity. So what we see is the simplest possible distribution, the normal distribution of modes with a given wavelength, and no evidence for non-Gaussianity. This again is staggering, that the universe on the larger scales is so extraordinarily simple. And then most interestingly, we see no evidence for gravitational waves, and that's very interesting because the most popular theory, the theory of inflation, it's the one thing it predicts, is that there would be gravitational waves, but so far this is consistent with zero. There's another way of looking at this, which is there are two scales in physics which we know of. The tiniest scale is the Planck length, and this is the scale which, if you tried to probe it with radiation of a short enough wavelength, then as you send the waves of light in towards the object you're trying to probe, or the length scale you try to probe, they would simply form a black hole, and you would be unable to see something that small because the photons you would be using would be so energetic. So as far as we know, we're unable to probe length smaller than this scale, way beyond what we can do experimentally. But the dark energy is so significant because it tells us there's also a larger scale which we can probe. The reason is that material which is any further away than this distance is being accelerated away from us by the repulsive gravity of the dark energy so rapidly that any light it emits will never be received by us. And this holds infinitely far to our future. We will only ever see a finite portion of the universe. And so this is the extreme length scale in physics. On the upper end, we simply can't see anything further than this distance. It's the Hubble radius defined by the dark energy density itself. And then the way the universe seems to work is that that the universe seems to be astonishingly simple on small scales. I'll show you some evidence for that, simpler than was expected theoretically, and again, astonishingly simple on large scales. The simplicity is at the two ends of the spectrum, and all the complexity is right in the middle. And if you take the geometric mean of these two lengths, what you get is 30 microns, which is about the size of a cell. And so we live in the middle between these two very simple extremes. And the reason this is so challenging to theorists is that theorists have been building models essentially like Lego, adding particles and forces and fields in a bottom-up approach where you start with the very smallest things and you just build up to the largest. And within that paradigm, there seems to be no hope of explaining this, as I will detail later. Equally, we can look in energy scale. So we can take the Fourier transform of the history of the universe, and the dark energy scale, the scale defined by, so this is the fourth root of the energy density in dark energy, is a fraction of a milli-electron volt. That's the smallest fundamental energy scale we know of in physics. And the larger scale is that Planck energy. Again, if you tried to create a photon of a higher energy, you would simply form a black hole. The Higgs, the only other fundamental energy scale in the physics we know is the vacuum expectation value of the Higgs boson. Okay, that is the only other scale that appears in the standard model of physics. And rather neatly, it's the geometric mean. It's approximately the geometric mean of these two as well. So this again is an indication that interesting stuff somehow occurs in between literally at the geometric mean of the two extremes in energy as well as in length. Here's all known physics in a line. It's a nice formula. This summarizes what was done in the 20th century. We've got Einstein's theory of gravity. We have all the forces, the electromagnetic, strong and weak forces, all modeled after Maxwell's theory, Dirac's theory of particles, and then we have the Higgs part of the Lagrangian. And really, this is everything, except it doesn't explain a few phenomena. It allows you to fit many things. So the vacuum energy appears in this term. The Higgs expectation value, which defines the scale of the weak interactions, also appears in this part of the Lagrangian. So those two mass scales. And then, of course, the Planck length comes out of Newton's constant. Those are the only parameters with dimensions of energy or length in this theory. On top of this, we have neutrino masses, which are a pointer to physics at much higher energy. So this is certainly very interesting pointer to physics, to a connection between particles and the Planck scale. And then, of course, we have the dark matter, which is so far unexplained. Let me talk a little bit about Higgs and how significant it was. So here is Higgs' paper from 1964, Peter Higgs' paper. Notice how long it is. I thought Einstein's paper on E equals mc squared was good, because that was only 3 pages. But Higgs went one better. His is only 1.5. It makes the prediction of the Higgs boson. There's a little bit of mathematics, and that's it. And here's Peter Higgs at CERN, looking like he knows what's going on. And I can assure you he doesn't. But he does know about this. And this is what we're after in fundamental physics. We're after theories like this, which can be expressed very compactly in terms of some very fundamental principles, and most of all, are testable in experiments like this. So here it is, the Large Hadron Collider, and the great discovery was this tiny little bump at 126 GeV, and I call it the discovery of the half century. It took half a century from the theory to the experiment to verify the prediction, because there's the discovery of the century, which I'm going to come to later. So, to conclude from this, we've looked on the larger scales, the whole universe, we've looked on the tiniest, and in both cases we found unexpected simplicity. In the case of particle physics, no supersymmetry, no new particles. The recent particle causing a lot of excitement in particle physics was a hoped-for particle at 350 GeV. It's just gone away. And so there seems to be nothing beyond the simplest thing you needed to give elementary particles their bare masses. So nature seems to have found a simpler way to operate, specifically to create a huge hierarchy of energy scales. So we have the Planck energy, we have the Higgs energy, and of course the dark energy scale, forming this huge hierarchy. And this hierarchy poses a huge challenge to fundamental physics. We do not have any theory which really explains this hierarchy. There are, by the way, some fascinating clues coming from the Large Hadron Collider, but they're not to do with new particles. This is the most puzzling stuff, the dark energy. Here's a picture of it. And taken at great expense from the most advanced telescope known. Its defining feature is that it's constant in space and constant in time, and it's invariant under Lorentz boosts. Summarized by saying it's Poincare invariant. This is the most invariant stuff you can think of. And so this means that if I run through the dark energy, it absolutely doesn't change. If I run at a brick wall, it becomes a pretty dangerous thing to me. But dark energy doesn't change at all, no matter what you do. in time and space, in velocity, it's always the same. And the strangest aspect of it is gravitationally repulsive. And that's why it's causing the universe to blow up. Its value is a massive challenge to quantum field theory, the 20th century paradigm summarized in that formula I showed you, because if you calculate the vacuum energy, the vacuum contribution to the energy density, what you get is a divergent integral. You get an infinity. It can be positive if there are more bosons than fermions, or negative the more fermions than bosons, as there are in the Standard Model. And so in the Standard Model, it actually turns out to be minus infinity. And that's a long way off the correct value. So we know various contributions to the vacuum energy. Here is the vacuum energy contributed by the strong nuclear force for example. And this is showing you those vacuum fluctuations of the nuclear forces. But, and they're very large. This number is very large. All the contributions are very large. Somehow, miraculously, they all add up to just 10 to the minus 120 of the Planck scale, giving you that hierarchy of mass scales of energy scales of 10 to the minus 30 that I mentioned before. And we do not know what imposes this fine adjustment. This is a crisis of the first magnitude for quantum field theory. And that's what gives me such hope, as I explained. By the way, I can't help but mentioning this beautiful work by Gentornino and Crittenden, based on some predictions we made in the 90s, that the dark energy not only changes the expansion of the universe, it causes a correlation between the density variations and the pattern you see on the microwave background radiation. Basically, because if you have a lump of matter, it has a negative gravitational potential well, and as a photon falls into it, the well is then stretched away by the dark energy, leaving you with a net blue shift in the photon which came through. And you can actually detect this now. It's at about 5 sigma significance, and so we have this independent check that dark energy really does exist. So let me now I've talked about the current state of play and our knowledge of the universe. Let me talk a little bit about the most popular theoretical paradigm called cosmic inflation. And cosmic inflation was based on the following idea, just that dark energy causes exponential expansion. So if we want to explain why the universe is so big and flat and smooth, well, let's exploit some dark energy. We're going to use a much higher density of dark energy than the one we observe today. We want this to operate at very early times and to blow up the size of the universe exponentially so that the part we see is a very small piece of the whole. And so this was the idea behind cosmic inflation in the early 80s, that we imagine we have some field. It's similar in principle to the Higgs field, but this one plays no role in particle physics. And it has a vacuum energy density, or dark energy density, which depends on the value of the field. So the idea is you start the field off up here. This vacuum energy will cause the universe to blow up in size, and then this field will roll down the hill and land at the bottom, and your inflationary energy will have gone away, but it will have created a nice big universe for you. So this is the size of the universe blowing up exponentially under the influence of this energy density provided by this inflaton field. One of the very beautiful side effects of the scenario is that it automatically gave you fluctuations in the universe. The universe didn't come out perfectly smooth. It came out of the inflation process with variations in the energy density from place to place. Why? Because this field is a quantum field, and it can fluctuate up the hill or down the hill by a little bit in different parts of space, so that when it finally rolls down to the bottom, the universe is not absolutely the same everywhere in space. In some places, that rolling happened earlier. In other places, it happened later. and that ends up giving you density variations of the type we need to form galaxies. So this was a very cute idea, and initially quite compelling. Only problem was that this requires a lot of fine-tuning, okay? That unlike Einstein's or Maxwell's theories, which introduced no new parameters into physics and gave many predictions, this theory introduces a free function into physics, which is untestable directly. The only way to test it is to look at the cosmological outcome, but you get to dial this free function. Unfortunately, you have to fine-tune this free function. You have to tweak the shape of the potential to get those density variations at the right level. You have to adjust the minimum of the density of the potential to give you the dark energy we see today. That's true in all theories. It's not a specific criticism of this one. But probably the worst is that you have to do this fine-tuning. You have to say the universe started off with this inflaton field displaced from its minimum. And you don't explain that, you just postulate that. Okay? Well, how do you explain these things? There was, for a while, some optimism that string theory, which was a radical theory intended to replace quantum field theory, was going to somehow lead to big advances in our understanding of cosmology. And inflation theorists who were trying to explain the arbitrariness of these choices first looked to string theory to explain this. Now, string theory has turned out not to be so much a theory as to be an infinite number of theories, okay? And the reason is that in string theory, some of the dimensions of space are curled up in a little ball, which we can't probe directly, but their size and shape determine the pattern of particles and the constants of nature, all those numbers I told you. So this was initially very appealing. Aha, we have a theoretical framework which might explain those big numbers. And maybe it would even explain why this inflaton field was displaced, might explain this fine-tuning. Unfortunately, things didn't work out like that. As far as we know, there is no reason within string theory to prefer any one of these arrangements to any other. So instead of a theory of everything, we have a theory of anything. And so then this was combined with inflation into this multiverse picture. Okay, so the idea was, imagine that I don't just have one of these fields, but I have all the fields you get from string theory, thousands or millions of fields. They're all fluctuating up and down this potential. Parts are inflating wildly, parts are rolling down. The whole thing is the most complicated possible arrangement you could ever imagine. And this is a picture, actually, this picture was made by Linde and collaborators, that different parts of the universe emerge from this multiverse with absolutely different laws of physics. And Alan Guth, the inventor of inflation, said that anything that can happen will happen in this multiverse, and it will happen an infinite number of times. And so the amazing thing to me was that that made some people happy. I mean, at some level, it's obvious that when you have a theory like this, it's not going to predict much. But that's the situation we're faced with. That inflation has evolved into this theory with no specific predictions, but instead it predicts a little bit of everything. Lots of problems. Singularity, by the way, got forgotten that inflation added nothing to the issue of the singularity. That's the deepest mystery in cosmology, how the whole universe came out of a single point. Surely that's fundamental. Neither inflation nor string theory have really shed any light on that puzzle. There's a Liouville theorem. So what does Liouville theorem says? It says if you have a Hamiltonian system with time-reversible dynamics, you are not going to be able to explain a rare process by invoking those dynamics, because as much as you will get inflation going forward in time, you will get deflation going forward in time. It's reversible. You can't explain a rare configuration of the universe using time-reversible dynamics. And one can show this in great detail. There's this eternal inflation, which is classically you just roll down the hill, but quantum mechanically you also go up the hill, and the regions that go up will inflate even more. And so the whole thing is wildly out of control, and most of the universe will be undergoing inflation all the time. And so that again is a kind of pathology. It means you can't predict anything. There's the fine-tuning I've mentioned. And the big one is that perhaps this isn't a scientific theory anymore. Well, I just want to talk about one of these problems, because I think the basic problem with inflation is actually one of intuition, that people simply accepted this fact that vacuum energy causes a repulsive field, repulsive gravity, and they said, aha, we can use that to blow up the universe. And there is a very basic conceptual problem with this, and I think the intuition is at fault. So here's the picture. We take a little piece of the universe, we put this massive vacuum energy in it, and we blow it up. Now the problem is that this part of space-time, this space-time we blew up, is not complete. You can study this within general relativity, and you can ask, where did it come from? How long did it take a particle which is followed back to the beginning of the space-time? And the answer is it takes a finite time to the beginning. And that tells you it's incomplete. It started. And if you try to complete it, so you can try to solve the Einstein equations with vacuum energy and backward in time, and this is indeed what you find. And that picture I showed you before is just some funny slicing of this picture, which doesn't include the deflating part. But the completion of the inflating solution is called de Sitter spacetime, and it has a contracting part and an expanding part. And to give you a little intuition to that, it's just like a spring. You see, if the question is, is it likely to find a spring compressed given some temperature, the answer is definitely no. I mean, springs usually at room temperature will look like that. It's going to be very rare that we will find the spring in that configuration. And it's similarly, the way you get up here is by compressing space-time, and then it re-expands. This is a very, very rare configuration in an inflationary theory. So unfortunately, the initial conditions people are assuming are extremely rare. But the problem they were trying to solve is the problem of how did we get this very unusual, smooth, flat universe. Unfortunately, they had to make an assumption which is just as bad as assuming you have a large, smooth universe. And Penrose has summarized this very nicely, that for some reason the universe is extraordinary, in this extraordinary special configuration, and somebody placed it there, and inflation doesn't explain that. Now, even more impressive, inflation is under growing pressure from the observations. So when we drew that picture of the potential, I told you it needs a bit of tuning to make things work. But you can try and fit this form, for example, with a quadratic or a quartic shape, and adjust the coefficients to fit the density fluctuations. But if you do that, you make a certain prediction, which is that it's not only this field which gets quantum fluctuations, it's the gravitational field itself which gets quantum fluctuations. And they show up as gravitational waves in the universe today, and they would be seen in the microwave background. So this is what the Planck, you probably know, there was this claim made by BICEP 2. They had detected gravitational waves from the Big Bang. All the inflation theorists got very excited. Stephen Hawking claimed he'd won his bet with me, and I owed him 200 Canadian dollars. He said this on Radio 4, on the Today program. And my response was, A, any experiment needs to be repeated before you believe it, especially one this fundamental. And B, the whole theory is so implausible and logically inconsistent that I would be amazed if that result was true. And so 3 months later, in fact, it was incredible that the theorists, you see, over the last 20 or 30 years, the theory community kind of diverged from observations, certainly with string theory. And I challenge you to look at that original BICEP paper, the one claiming this detection, and not to see there are immediate problems. I mean, anybody, you read the abstract and they say we can exclude dust with 2 sigma confidence, but we claim a 6 sigma confidence for the result. I mean, it's in the abstract of the first paper. Somehow people didn't notice that, and I take that as a huge failing of theorists, to be willing to accept something just because they wanted the result. And I'm afraid this is rife, okay? So here we have the Planck collaboration working with BICEP to exclude this claim. And what's happened is that if V is phi squared, so just a simple quadratic potential, that's the black dots, and the data of the Planck satellite and the BICEP, when combined properly to account for the possible presence of dust, actually do a very good job of excluding this theory, proving it wrong, not right. The point I was making about theorists is that none of these theories actually make any sense. I mean, if you just graph phi cubed, this doesn't have a minimum, okay? Neither does this one. There's no explanation for what happens when phi goes past 0 in this theory. These are not really acceptable theories, but nevertheless, people like plotting something on a curve. The only one which fits is this R-squared inflation, which is theoretically inconsistent, wildly inconsistent. It's the analog of the runaway electron, which you can read about in books on electrodynamics. This is an artifact of a theoretical error. So the only theory that really works is one based on a logical error. So it's a very, very interesting situation. So that, of course, has encouraged me to try to rethink this. How are we going to do better? We have this amazing situation. The universe is speaking to us, telling us how simple it is, and at the same time, theory has exploded, has blown up in our faces, and said it can't predict anything, it could give everything. We have this wildly out of control inflationary process, which we're hoping will somehow sort things out. So I think all that's very likely wrong. And there is a very important role now to rethink all of this and see, where did we go wrong? And for sure, the answer is going to come from quantum gravity. At least that seems evident to me, is that we don't really understand how quantum mechanics connects to gravity. Our calculations of the vacuum energy are all wrong. We don't know what happened at the singularity. We've seen singularities before in physics. There's a singularity at the center of the hydrogen atom. The electron would have fallen into that singularity, but for the effects of quantum mechanics, which prevents the electron falling into the singularity. And so, this is what quantum mechanics should do, and so far it has not. So let me tell you a little bit about quantum gravity. Quantum gravity is a very mysterious and wonderful theory, which is the ultimate in minimalism. Okay? There is no time in quantum gravity. In quantum gravity, the energy is zero. That's a statement, that's an operator statement in the theory, that the total energy is zero. By the way, completely misrepresented in Lawrence Krauss's book, The Universe from Nothing. If you read that book, it's really, really strange. He claims that observations show us the energy is zero, and therefore it could have been created from nothing. This is wrong. In gravity, the energy is always zero for any state. Any state you observe would confirm that the energy is zero. It's just a fact that the energy must be zero in the theory of gravity. It's because it doesn't have a preferred time. So quantum gravity works by saying I've got some geometry, some 3 geometry, meaning a space with some matter in it, and I want to calculate how a given configuration of space and matter, how it gets converted into another configuration, and I want to know the amplitude for this process, the quantum mechanical amplitude. So there have been many beautiful theoretical works, but interestingly, the most basic conceptual problems remain unsolved. Namely, what determines the wave function in quantum gravity? You have to specify boundary conditions on the space of these geometries, and that is still open. What is the probability? Any quantum theory, you say, I need to know a formula for the probability. Quantum mechanics, it's the modulus of psi squared. But in quantum gravity, this is unknown. What is the formula for the probability? And by the way, string theory does provide some kind of theory of quantum gravity, but it only works in completely unrealistic settings, like flat space with no matter density, or anti-de Sitter space, which is de Sitter which is the opposite of de Sitter space-time. So string theory, unfortunately, hasn't shed much light. So in a very recent work with Stefan Gielen, we realized something amazingly simple, which is if you take pure radiation in a Friedmann-Robertson-Walker universe with a metric like this, A is the scale factor, and I work in these conformal time units, then it turns out that the space-time metric classically looks like this. Now that's a very interesting space-time. You see, all I have here is some given static metric. For example, it might be Minkowski space, multiplied by this factor t squared. What's that telling you? It tells you that as I go back towards t equals 0, the size of the universe shrinks to 0, and then what do you know? It reappears as positive again. That's a bounce. So the universe bounces if there is nothing but pure radiation. The only requirement is that the stress tensor is traceless. Pressure is 1/3 rho. So what we showed in this paper is quantum cosmology is actually exactly solvable in this case. We could calculate the Feynman path integral exactly and show that this bounce happens in the quantum theory. And space-time is fuzzy near the bounce. There's no real meaning to the size of the universe near the bounce because it all gets fuzzed out. We called it a perfect quantum cosmological bounce. And we were able to show you can follow perturbations across the bounce. You need to view the scale factor of the universe as a complex number, not a real number. It's not a classical thing anymore. And you know in quantum mechanics, classical variables become operators. The best you can hope for is that they are represented by complex numbers. And so in a semi-classical process, one that is disallowed classically, those variables are complex, and that's what happens. The scale factor A can be tracked across the singularity, but only by going into the complex plane. And if you do that, you can follow the perturbations all the way across the singularity or around the singularity and see how they go through the bounce. So that's the simplest model of a pretty realistic universe, a radiation-dominated, Friedmann-Robertson-Walker, and we believe we can study what happened at the singularity. And there was a bounce. Now, the next ingredient, so this is in unpublished work, the next ingredient is to add the dark energy. what's the role of dark energy? And this does something really amazing. Okay, so I'm very excited about this. It's not published. It may turn out to be wrong, but this is very cool if true. The Hamiltonian for the universe. Now it's a bit strange. The size of the universe, think about it as if it was the position of a particle, x, and the Hamiltonian for a particle would have a plus p squared. Well, the scale factor of the universe happens to have the wrong sign Hamiltonian, the minus sign. That's probably why the universe is not static, because gravity is unstable. So that's the minus sign that explains the expansion of the universe. This is the momentum corresponding to A. Radiation density comes in like this. This number is a constant in the background, cosmic background. So think of this as just a constant, this combination. And then we have the dark energy, which is a positive and growing contribution to the Hamiltonian. So just as in quantum mechanics, we turn this into a Schrödinger-like equation, and it looks like this. It looks like quantum mechanics in a negative a to the fourth potential, okay, where the radiation energy is the energy, the quantum mechanical energy in the system. So one way of saying this is that the total energy, combining all these terms, is zero, as I explained before. So let's forget about the radiation. We just have scale factor and cosmological constant. This is what the system looks like. So imagine I'm at some particular, and I have to be at zero energy, right? So I'm interested in the zero energy trajectories in this potential. So take the trajectory where the particle is running outwards to the right at zero energy, and just follow it back in time. So classically, it's very obvious that it will take an infinite time to reach zero, because the potential goes flat, and the kinetic energy of the particle just runs out of steam, and eventually it would hit zero. So that's the classical behavior. Quantum mechanically, it doesn't do that at all. Quantum mechanically, you tunnel through such potentials. And these are the quantum mechanical solutions. So it's saying that in a universe with only dark energy, you would, again, go through a bounce. But the bounce happens because of quantum mechanics. It's a very interesting universe, because the energy density in the universe is finite throughout this process. So some things to say. What determines the wave function? Well, we need a complex wave function. As anyone will tell you in quantum mechanics, a real wave function will never describe a particle in motion. If the momentum of a particle is not zero, you have to have a complex wave function. Strangely, almost all other proposals fail this criterion. They don't describe an expanding universe. The no-boundary proposal, the proposals coming out of string theory for the wave function, impose Dirichlet or Neumann boundary conditions here. They give real wave functions. They don't describe an expanding universe. It turns out that Feynman's path integral naturally selects this state. There's nothing else you need to do. You write down the path integral. It's constrained by various symmetries, and it naturally selects this state. The wave function passes smoothly and unambiguously around the singularity, and A tunnels through. Now, the really exciting thing is what happens at large A. After all, that's the big mystery in the universe. The universe is going to infinite size, dominated by dark energy. What does that mean? We'll never see beyond some limit. So the universe is finite, but it somehow has this mysterious infinite future ahead of it. Very, very strange combination. Now you notice this wave function is decaying as I go to large A. And that's obvious in WKB. If you remember WKB, you do e to the I integral p dA. P goes like A squared. And there's a 1 over root p, a normalization factor here. What it means is very significant. It means that the probability of A, psi star psi, is actually normalizable. The 1 over A makes it normalizable. The presence of dark energy makes quantum gravity make sense. Okay, so this was never observed before. It seems like a very basic fact. But what it means in particular is that the expectation value of the metric doesn't exist. If I have a probability distribution which goes as 1 over a squared, and I take the expectation value, it's a good probability distribution, but the expectation value of a squared is infinite. So you cannot deal with such a universe in pretending that the metric is a expectation value of some quantum metric. So the implication is that space-time is very random in large scales. It's not unlike the multiverse, but the theory makes sense. So here's the quantum cosmological bounce that we described. The universe comes in, it shrinks. Whether or not there is radiation, it shrinks and re-expands. Here is time. This is the physical size of the universe. What's sort of more interesting is the causal structure of the universe. As I look back in time, I can see the Big Bang singularity. And it's very natural to suppose, at least within this framework of quantum gravity, it's very natural to suppose that the space-time configuration on this 3 surface is actually the same as the one over there. And the path integral directly gives you the probability of finding this configuration. So I realize this will sound a little bit mysterious, but which it is, but it's also quite exciting. We have shown, in fact, that this Feynman propagator is problematic for open universes, meaning that the theory is just inconsistent if the universe is open on large scales. And that suggests maybe a new explanation for the flatness of the universe. Not a classical dynamical process like inflation, but a much more profound quantum one. It's rather easy to introduce a new mechanism for generating the kind of perturbations we need to explain galaxy formation. In fact, they seem much more natural in this context than in inflation. And I think there's a real hope, though, of a much more minimal and predictive cosmology, which isn't saying much, because the current trend is completely unpredictive. But the direction we're heading, I think, is towards a much more minimal and predictive class of theories. Now, I've run out of time, but I want to show you a movie. Because I claimed in the beginning that we will be able to test all this. And what gives us hope is this discovery of the century, the observation of 2 black holes merging, the detection of gravitational waves, announced earlier this year. And so I'm just going to show you this movie. So imagine you are now in the very early universe. You're, let's say, 10 to the minus 10 seconds after the Big Bang. You have these random density variations floating around. They're sound waves. The question is, what do those sound waves do? And is there any way in which we can access them today? Can we see the sound waves in the early universe directly? Gravitational waves allow us to look past that red circle back into the early universe. But do these sound waves emit any gravitational waves? If they do, we will be able to see them. So let me show you what these sound waves do. And actually, we learned this, strangely enough, studying perturbation theory and quantum cosmology. It's a completely classical phenomenon, but it had been totally overlooked. Sometimes just by working hard, you find things out. So here are these waves, and here they go. Okay, so these are sound waves moving along in a perfect radiation fluid in the early universe, and you see what happens. They form shocks. And so any fluid dynamicist would probably have told you this would happen, but cosmologists didn't realize this was happening in the early universe. We now know this to a high degree of confidence, this was taking place. And it turns out these shock wave collisions emit gravitational waves, which can be detected today, by detectors today. And I'll just show you this, end on this picture, that waves produced at the Planck time, very near the Big Bang, would be about millimeter wavelengths today. So if we build gravitational wave detectors at that scale, we will see them. Gravitational waves produced before nuclear synthesis would be light years today, just before would be light years today, and we can already use them to severely constrain the state of the universe at that time. So it's not at all hopeless to look for observational tests of such fundamental theoretical ideas. So thank you for listening.
So thank you, Neil. We are almost out of time, but we do have time for a couple of quick questions, and the gentleman there is obviously very keen to ask one.
First of all, thank you very much, Neil.
Thank you very much. Very interesting, very interesting lecture. Question, what happens to your rulers and clocks in the pre-Higgs era?
Yeah,
because where maths is...
It's a great question, and I was alluding to this when I mentioned one of the most surprising discoveries of the Large Hadron Collider. The LHC discovery is pointing towards scale invariance at high energies. Okay, so scale invariance means that the theory, the standard model, becomes like Maxwell's theory. See, Maxwell's theory is scale invariant. That's why a radio wave is like a light wave, is like an X-ray. They're all the same because the theory doesn't have a scale. And they all behave in exactly the same way. So there are hints now that the standard model may also have this property, that at high energies, there is no scale in the theory. That means there are no rulers. There's no preference of one scale over another. And that itself, that's why we studied this quantum cosmology. We studied quantum cosmology in a fluid which has scale invariance. T mu nu is 0. And that's the one which resolves the Big Bang singularity. See, if you want to understand what happened when the size of the universe was 0, the best chance you've got is to look at a theory which doesn't know about the size.
Yeah.
And that's what seems to work. So it's very fundamental, and I would say, the suggestion is the laws of physics have no scale at high energies.
Okay, perhaps one more question before we get thrown out.
Do I deduce from what you said that the universe therefore had, in this model, an infinite negative time?
And also a good question. No. So my current belief is the following, and I sort of hinted at it here, is that, you see, we're trying to explain this amazingly economical universe, right? It has almost no numbers describing it. We need a theory that's equally economical. A theory of the multiverse is the least economical theory, but equally a theory which is cyclic, which I have been keen on, also has a lot of arbitrariness. I mean, there's a chicken and the egg problem. What came before? And why was it like that? Well, something before, and so on. And there's a logical, problem with that. It's not an extremely simple theory. So can we make a simple theory? And I think that we can. I think that the way that quantum gravity works cries out for the following, which is that I say, I want to study the amplitude to get a universe here, a 3 geometry out here. So I want to know that amplitude. Basically, the Feynman path integral gives you the vacuum amplitude. So what I'm saying is the universe is in its vacuum state. This is the minimal state that we're in. But what about before the Big Bang? Well, what the path integral cries out for is that this state is exactly the same as that state. Okay, so it gives you an amplitude for that state, and you can calculate it at this end or at that end. It just gives you a number, and that's all you want. So my current hope is that when we go through the Big Bang, indeed there was a bounce, but what came before the bounce is exactly what came after it. It's not a mirror image, okay, because there's no rigid mirrors in gravity, and the only thing that's mirrored is the final state, not the intermediate state. So I think there is a prospect that will work. It will certainly be an extremely economical prescription for what the state of the universe is. And in fact, I'd go further. I think this picture should explain the emergence of time. Why is there an arrow of time? That comes down to something extremely fundamental in gravity, which is this, that the metric is the square of A. So when I represent a 3 geometry, I can use A or minus A, and one copy is A, one copy is minus A, and if you have a 4 geometry going between them, it has to pass through 0 somewhere. That's why there was a Big Bang, and that's why there's an arrow of time. Okay, so those are the long-term goals of this program.
We are well out of time, I'm afraid, so we just adjourn to the drinks reception in the library and to the next meeting on Friday, the 11th of November. And we thank Neil and the other 2 speakers for 3 very excellent talks.
Thank you.